So in this video, I want to talk about the rules for dealing with currents and voltage in series and in parallel circuits. Now, current is constant in series, and in parallel, it's divided between the branches. While voltage is constant in parallel, and in series, it's divided across the circuit elements. These are some good rules to memorize and make simplifying and analyzing circuits a lot easier. But in this video, I want to talk about why they exist, why this comes up. We're going to start with current in series. So current stays constant in series because basically current is made of moving charges, and in series there's only one path for the charges to take, so the current has to stay constant. Basically, if the current weren't constant, then a bunch of charge would build up somewhere. But of course, if a bunch of charge builds up somewhere, then it's going to repel itself, and so it's not going to let itself build up. It's kind of a self-regulating system that current stays constant in series. Now, on the other hand, if we have a split in our path, then that means our current is going to have more than one path to take. And so that current, that charge, is going to split among the paths. Now the total charge is conserved, so the total current going into one path is going to be the same as the total current going out. And you can see that we have 110 milliamps coming in here, and leaving that junction, there's a total of 110 milliamps going through those three parallel branches. So the total charge is conserved, total current is conserved when our path splits. So our current is divided in parallel. And it's divided based on the resistance of the paths. The more resistance we have, the less current we're going to get. And the less resistance we have, the more current we're going to get. And we can actually use Ohm's law to figure out how much current is going to take each path if we know the voltage and the resistances of each path. We also know that for constant voltage, current is inversely proportional to resistance. So if you have twice as much resistance, you're going to have half as much current. We can also see that the current, here we have 20 plus 30 plus 60 milliamps in each of the branches, and they all combine back together to 110 milliamps. So the total current still does stay constant, it's just that it splits and recombines in parallel. Voltage, on the other hand, is constant in parallel. That's because voltage isn't, well, voltage is, again, it's potential difference. And potential difference is like change in potential energy, but it's change in potential energy kind of based on something like height. For gravity, potential is just height. And on a wire, an ideal wire has no resistance, which means it's going to be an equipotential surface. And any conductor, in fact, is an equipotential surface if it's a perfect conductor. So that means that all along this conductor on the top, it's the same amount of potential. And that means that all along this conductor at the bottom, it's the same amount of potential. If I go from one potential to another potential, the voltage is just the difference between those two numbers. And it doesn't matter where I come from on the orange to get to the cyan. It's always the same number, whether I pass through this resistor, this resistor, this resistor, or this battery. So no matter what, since we start at the same height and end at the same height in parallel, that's the same potential, that means the potential difference across all of these resistors, all of these circuit elements in parallel has to be constant. So voltage has to be constant in parallel. In series, voltage is divided. Well, we know that the total voltage has to be constant in parallel. That means if we have 120 volts here, we lift up 120 volts. It has to fall back down to 0 volts by the time it gets to the bottom. Otherwise, we would have two different numbers for the potential on this bottom wire. So that means each time we cross one of these resistors, we're going to go down to a lower potential. Of course, a larger resistor, a resistor with a greater resistance, is going to dissipate more energy. And remember, potential is just potential energy per unit charge. So if you dissipate more potential energy, then that means you're going to have a larger potential difference across you. So our 120 volts here is divided between these two resistors in series. It's got to cross back all the way down a total of 120 volts. And that voltage drop across these resistors is proportional to the resistance. More resistance, more energy dissipated, means more voltage, more potential difference. So I hope that helps a little bit to explain why these rules apply for voltage and current in series and in parallel.